Hey there, my name is Alejandro, and welcome back for day 160 of me doing the Daily LeetCode Challenge until I reach 1 year's worth of good contributions here on GitHub. So today's problem is for December 23rd, 2024. Let's get straight into it. Okay, today we get a LeetCode medium problem 2471, minimum number of operations to sort a binary tree by level. You are given the root of a binary tree with unique values. In one operation, you can choose any two nodes at the same level and swap their values. Okay, so you can essentially do like a bubble sort. Okay. You can swap. So okay. Return the minimum number of operations needed to make the values at each level sorted in strictly increasing order. The level of a node is the number of edges along the path between it and the root node. So is the number of steps needed going to be like, the number of incorrect positions, or like, it's like you're going to go through and you're going to be like, okay, this guy's not at the right spot. Put it with the guy that is at the, swap it with the guy with the right spot and keep on going. Okay, we can do something like that. Also, we can map, each level to essentially its list of its nodes and in order. Okay, so let's rock and roll, ladies and gentlemen. For reference, I've done. I'm happy. I'm super happy because I just finished day 21 of the Advent of Code challenge, December 2024, and it's gonna be a 6-hour video once that releases. So. Yeah, fantastic. Not quite as long as day 20, but still a lengthy little problem. And I haven't even started day 22. Problem 23 comes out in 4 hours, so I'm like, I got to catch up. But thankfully, that finishes day 25, and I can just go back to my normal daily LeetCode challenge routine, which is much more familiar and much more integrated into my life. But okay, nevertheless, let's keep on going. Let's do Q is equal to collections.deck. Here we'll do... with the root node, and here we'll say, so let's do a BFS of the tree, because here we want things by level. So there we go. We can even do a DFS. We can actually do a DFS totally fine, right? It's just like, for each, in fact, we can, let's just do a DFS. Or, well, okay. If we do a DFS, right, we can do DFS. It takes in a root, and here it's like, okay, if not root, then return. Here it'll be like, here we'll have a dictionary, and then here we'll say like, here we'll say, if root.left, or here we'll say DFS of root.left, DFS of root.right. Actually, no, we can't DFS. No, we can DFS if we put a depth. Depth plus 1, depth plus 1, and here we'll say, it doesn't matter where we do it, post order, in order. Here we'll just say D of, so here we'll make this a default dict of list, and here we'll do D of root of depth dot append root dot val, right? And here we can just do something like print D, right? And here if we print D, okay, here, you know what, we'll do self.d. That's not the problem. The problem is this. You do DFS from the roots. There we go. So now we have essentially, level 0 has the node 1, level 1 has the nodes 4, 3, then we have 7, 6, 8, 5, and so on. Essentially, so now what we need to do is we need to take in, so this is essentially, we can do this in a DFS kind of way, but I prefer usually doing a breadth first search kind of way. So here we'll do it the breadth first search kind of way, just because when we do level order, I just like doing it this way. Here we'll do collections.deck, while length of Q, we'll have the root in there, root with a depth of 0. What does it consider this depth as, or level? Here we'll say node, level, right? See here, it says this is the second level, so it says that this is level 1. Okay, sure. What length of Q is greater than 0? Here we'll say node, level equals Q dot pop left, and here we'll say, okay, we'll say if, here we'll say D of level dot append node dot val. Here we'll say if node dot left, Q dot append node dot left, level plus 1. If node dot right, here Q dot append node dot right with level plus 1. Okay, and then here if we do print d, we should get the very same result, right? So essentially, yeah, so level 1 we have 1, then we have 4 and 3, then here we have 7, 6, 8, 5, and 9 and 10, right? So okay, there we go. So I just prefer doing things the BFS kind of way. It doesn't matter. The point is that, like, you know, I just showed both just because, you know, why not? And let's just keep on going here. Here, what shall we do? So yeah, so get num swaps needed to make sorted, right? And here we'll just return sum of self.this of level values, or level values of values in d.values. Right, there we go. Okay, now we just do this, and here we'll say nums get num swaps needed to make sorted, right? Okay. So now we essentially have another problem within the problem. Okay. So now it's like for each of these, it's like, okay, get, you know, number of swaps needed to make sorted. So one way we could do it is sort the actual list, right? Another way we could do it is by prefix mins and maxes, right? Where it's like, you know, for each index, essentially get the next smallest index kind of idea. Which for that type of stuff is usually, you know, a good thing is a monotonic stack. So we can do something like that. So that way it's like, you know, instead of sorting, one way is essentially just sort nums, right? And like, you know, get the indices of everything and so on. That's kind of a boring solution though. Here, what can we do? We can, yeah, so essentially, index I and nums want to find smallest index j such that I is less than j, and such that nums of j equals min of nums from I plus 1 onwards to n. Okay. So essentially what we want to do is, yeah, here we'll say for I in range suffix mins is equal to this, min val equals float of infinity, range length of nums minus 1, negative 1, negative 1. Here we'll say of min val nums of 0, and here we want this value to get, yeah, so here we'll make this a collections.dec, and here we'll say suffix mins dot append left the min val, right? Print f string nums equals print f string min val suffix mins equal. min index equals nums of I. If num less than min val equals num, min index equals I. Min val, min index. We want to print this. Oh yeah, return 0. Also, this takes in itself. For now we just return 0 no matter what. Right, there we go. So yeah, 9 and 10. So the smallest from this index is that. So yeah, so let's look at something like this. The smallest from 7 is 5. The smallest from 6 is 5. The smallest from 8 is 5. Yeah, this is good. This is good. This is good. Oh, but then it keeps changing. The point is when I swap it changes. So yeah, I can't do it this way. Yeah, monotonic stack doesn't work because I keep swapping the things, right? Yeah. Yeah. Maybe I have a heap of all the remaining elements, but then how do I get rid of the element? I guess I could use a visit set and so on. Like, there's a way to make this O of n. For sure. Yeah, there's for sure a way. I mean, one way is essentially I sort this, right? Sorted nums. Sorted of num comma I for I comma num in enumerate nums. I comma num and enumerate nums. We will say if num doesn't equal sorted nums at index I, num comma index 0 comma 1. Or more importantly, if I doesn't equal sorted nums I of index, here we'll do printf string sorted nums equals printf string nums equals, and here turn 0. Right, so as I look at something like this, I'm like, okay, this should be the value at index 3, right? So here's like, okay, this is index value 0. So you get swap with whatever is at index 3, right? And so then index 3 is in its right spot. Yeah. So here I'll say, if this index doesn't equal to the index that's in here, then sorted index equals sorted nums of I of index. So yeah, we need this for the sorting. Index doesn't equal sorted index. Nums of sorted index, nums of index, right? So here it's like I have nums at index 0, which essentially become nums at index 3 here, and vice versa. So I'd swap the 7 and the 5. Because I need the 5 to go here. It's like here I need the 6 to be here, and it's already there. Here, need the 7 to be here. It's like, oh, it's an 8. Right? So here it's like, oh, I need the thing that's at index 0. Oh, but it just got swapped. Right? Maybe I just fixed the other one, right? Yeah, so the point is that I just need to solve this little problem, right? During the minimum number of operations needed to make values at each level sorted in strictly increasing order. Choose 2 nodes at the same level and swap their values, right? This feels like bubble sort. And it's any 2 nodes, right? So I need to put the minimum one on the left. Right, so this would be n squared, right? But I don't have to do this n squared. And I don't know if I can just return the number of incorrect positions divided by 2, right? Or something like that. The point is that, like, maybe it would be easier if we just did num. But can the numbers be duplicates? All the values of the tree are unique. Okay, that's all we need. So that I was doing based off indices. Note that all values in the tree are unique. So don't need to do things based off indices. Okay, that actually just makes things a lot easier to think about. Not easier to or just code and so on. It would still be the same when you do it based off indices because indices make it unique, but yeah, the numbers are unique themselves, so we can just basically do things right away, right? So here we can get rid of this. Yeah, for index and num. Yeah, so for num and nums. Sorted num is equal to sorted nums of I. If num doesn't equal to sorted nums of I, but maybe the I and num was kind of useful, right, though? Yeah, maybe the indices was useful though. Because I need to swap, or I can just mark them as good, right? Made good is equal to a set. If num and made good, continue. Otherwise, sorted num is equal to nums of I. If num of I doesn't equal num, res is equal to 0. Res plus equal to 1. Sorted num. Made good. Wait, no. Because here what I'll do is essentially I'll swap 5 with the 7. But it doesn't mean that this was made good. Can I just return that? Like, what if I just do this, right? Let's just try this. I don't care about like in range length of nums. Right, what if I do something like this? Because I'm getting confused for no reason here. No. Mat.seal, if anything. Right, so if I do something like that, yeah, okay, it's just, okay, I gotta be, like, not too cheeky here. Oh gosh, also, I should start practicing to try to get this answered in the first try. It's just like here, I'm just getting impatient, right? It's just, I'm like, I know what to do, and it's just, I'm getting impatient. I shouldn't be getting impatient. I should just solve the problem, be tranquil, and so on. There we go. There's no need to rush this. There's no timer, there's no nada. It's just, yeah, let's not be frustrated. Get num swaps needed to make sorted. Then yeah. So yeah, here we can probably do num, I, right? This was really useful. Or here, so here 5 belongs at index 3. And then I'll get the 8. Yeah, so this is what I need to make. So yeah, this is not what I want. Sorted num, sorted index equals sorted nums of I. While index doesn't equal sorted index. At the beginning we have 0. We're going to say well, index doesn't equal sorted index, then we'll swap, right? Here we'll do num swaps. Right, at the very end we'll do return num swaps. And range length nums. Index equals I, num equals nums of index. Okay. That way it's like we don't mess with this. Sorted nums, sorted index. Yeah, well, index doesn't equal to sorted index. Then we're going to do nums of I of index, comma nums of sorted index. So yeah, the one at 0 and 3 will swap. So the 5 and 7 will swap. I know, but these are the original indices. Okay. We gotta look at the number in here. Right? So let's think about it. Index and num is equal to 7 and 0. Why is this so hard for me to think about? 7, it's like, what do I do with 7? I don't know, but what you need is 5. which is at index 3, right? Nums at index and nums at sorted index. Nums at index and nums at sorted index swap. Num doesn't equal sorted num. And we'll do nums of index. At index 0 and index 3 will swap. So then we'll have nums is equal to 5, 6, 8, 7. And here it will equal, here it will not. And so here we'll still have 7, 0. And here it thinks it's at the index 0, but it's no longer there. So yeah, that's why the index stuff is useless. Oh. Why is this so like I just don't capiche here. The level of, like this was the same thing that happened to me in the contest. Some triviality like this, and it goes right through my head. Number of bit flips, number of swaps. It's just I hate these. Return the number of operations needed to make the value each level inserted strictly increasing order. Okay. Oh gosh, okay. I literally have what I want it to become. I need 3, 1, 0, 2. Like it would be so much easier if you can make this swap. Like it's just you can make the swaps anywhere. Oh gosh. No, the point is like my hand is forced. I must put the 5 here, just that the 7 will be here. So yeah, what I need is this. I need a num2 index. Right? So sorted nums equals sorted nums, literally. Continue. Otherwise, here we have a discrepancy, right? So our current number doesn't equal the one at the index. index of num to index of nums of I, right? So here if I do string num, comma, sorted nums of I, comma, valid idx, comma, valid idx. Let's just help my brain here. How's this wrong? Yeah, that's where it's wrong. That's where it's wrong. And nums of I. Here we'll just do sorted num. To index of num equals sorted index. Num to index of sorted num equals num index. Print a string num to index equals this is terrible. Oh my gosh. Okay. Yeah, here we gotta do this. Okay. Let's relax here. It's just terrible. They didn't do anything. No, if it's equal, then we don't do anything. Now here, what is going on? Print it once, print it once. How am I not switching it? Oh, because I do it again. Yeah. Yeah, the point is we only want to do this once. Made good dot add num. Sorted num. If num in made good, continue. Made good equals set. Yeah, so that's the point. Yeah, there you go. 0, 1, 2, 3. Yeah, so prints can become hashtag prints. Okay, that took just too long to do. Okay, let's submit. And wrong answer. Okay, so we should do this in a better way. Oh gosh. Or sorted num in made good. Yeah, I need to figure out. Okay, it's just one thing. Get num swaps needed to make something sorted. Get minimum number of swaps needed. So it's like, okay, it's either DP, greedy, or divide and conquer, right? Ideally, I'd like it to be linear. If I do linear, my entire solution to the entire problem is linear. Right? I need to traverse the tree anyways. So I'm allowed to make this linear. If I make it n log n, it is what it is. Right? Or let's think about the input size here. Then yeah, I can make this O of n or O of n log n. I cannot make this n squared. Okay. I see why this is a medium. Traversing a tree is not hard. Doing the thing is hard. Return the minimum number of operations needed to make values at each level sorted in a strictly increasing order. You can't bubble sort. Yeah. Right, the point is that what I want is essentially to index I, num for I, num in enumerate nums. I, num and enumerate nums. I continue. Otherwise it doesn't. Nums of I does equal sorted nums of I. Equals sorted nums of I. This is just cheeky. Yeah, if it's already in place, then good job, right? Otherwise, yeah, assert I is less than. Num to index is equal to this. Index to num. For correct index, num in sorted nums. Yeah, this is how we should go about it. We'll say correct index if num to index num equals correct index. Continue. Otherwise, this doesn't equal the correct index. Otherwise, yeah. So yeah, so this num, we know its correct index. That should go to. Index to num a correct index. Now we want to make a swap. We want index Alright, why is this confusing me? Here's the number, and here's the correct index it should be at. Let's get the numbers index. So we'll call this the num index. If the num index is the correct index, then good. Otherwise, num's index should be made to correct index, which obviously requires a swap with the number that's actually correct index. So that's why we do that. Num a correct index equals index to num. Make a swap. So num index 1, num1 equals num index num index 2, num2 equals correct index num at correct index. Assert that this is equal to num1 next to num of id x2 equals num2. Assert that num2 index 1 equals id x1. Assert num2 index of num2 is equal to x2. Num of id x1 equal to num2 to num of id x2 num1 num index of num1 equals id x2 num2 index of num2 id x1. num swaps plus or equal to 1. And here not return 0, but num swaps. Enumerate sorted nums. Okay, so now everything's correct because I took the time to just do it, right? So there we go. Completion streak 160 days, consistency is key, see you tomorrow. So here all we did was focus on just do it, don't panic, just make it work. Even if it's not efficient, well, in terms of big O time, it's just the expensive part is really this, but it's fine, right? Okay. The point is that, like, you know, we recognize that we can do it in log n, and it's totally okay, right? So people took 153, I took 232. So yeah, like for example, I can just start making this, right? And this will probably be okay. Well, that'll definitely be okay. But yeah, here I can probably just get away with one of them, right? So here's like, okay, can I get away with this, or is it the other one that I can get away with? I guess not. That's fine. It's okay. It's totally okay. Nums num2 index of num equals I, index 2 num equals num. Num2 index 2 num, dictionary. Sorted nums. Okay, this is useless. Okay. This is all useless. Okay. This is fine. Okay, run this again. Okay, there we go. Submit. Okay, 35%, so on. We could make it a little faster. People are at 153. We could, yeah, we could technically make things a little bit faster, but it's all right. Yeah. I wonder if people are doing this without sorting the numbers, right? That's the only thing, because then it means like I didn't actually get the full thing that I needed to get out of this problem. Yeah, I'm sure there's no... Right, one thing I could have done is like, you know, I can do the prefix mins idea as, or maybe not, I don't know, like maybe there's just a better way to do this, right? Or at least with this. Right, maybe I can put the indices in there and so on. Let's just like compare it in there instead of doing a hash map lookup every single time. Yeah, I mean, this is fine. We can submit one more time, and there we go. Like, it is what it is. That's okay. We're right here and so on. People are just getting like, 20, 30 ms faster. So I'm guessing that like people probably just did it with the sorted. It's just that they did the O1 stuff more efficiently, which I don't mind. We can just leave it as is. So bada bing, bada boom. There we go. So as always, in all my videos, I do a quick recap if I was able to solve the problem. So for this one, it was rather simple. It's just that I was just getting too... trying to get too hasty with writing the logic for this function. So it wasn't until I was like, okay, let's stop trying to be quick. Let's just relax, just write it. There we go, that I was able to solve it. So I'll go over how I was able to do it. So the very first step is like, okay, we need to essentially map, every single level in the tree to a list of its nodes, right? For example, this is level 1. It should have a list with just the value 1, right? Here's level 2. It should have a list with just the values 4 and 3. Here is level 3. It should have a list with just the nodes values 7, 6, 8, 5 in that order, right? And the way that I did that is essentially I just did a BFS traversal of this tree, right? So here I'm going to have a double-ended queue, and at the very beginning I'm going to have the root node with a level of 1, and here I'm going to say, okay, well, the length of the greater than q is greater than 0. We're going to pop, from the left, we're going to get the node and the level at the beginning with the root and 1, and we're say, okay, we're going to look at the level instead of our dictionary. So here's where we're going to map every single level to a list of all the values. And here I do a default dictive list. That way if a value is not in there, or if a key is not in there, it initializes the value to be an empty list. Here we're going to say, okay, let's look at the dictionary at this level that we pop this node from and append the node value, right? So starting with level 1, it'll be like, it'll be an empty list. We append the value 1, so we'll have just 1 in there. Right? Then we're going to say, okay, from this node, does it have a left child and if it, does it have a right child? If it has a node child, a left child, then we're going to append that left child. And what's its level? Well, for example, if this is a level 1, its left child is at level 2, right? So we do level plus 1. Same thing for the right child. If this is at level 1, this will be at level 2. If this is at level n, this is at level n plus 1. So whatever level we're at, we just do plus 1 for these. And the point is that we add the left and then the right, so that way we'll pop the left from the queue first and then the right from the queue. So that way when we add the values to the level inside of this list, we add them in the order of like the tree from left to right, which is exactly what we want, because we want to make that whole thing sorted in increasing order. Or if you did the whole thing in reverse, you can just do the same thing. But again, you want to, like, if I did the reverse order here, right, here I would get the solution to be wrong, right? But what I could do is just come here and sort it nums. And here we can just do reverse is equal to true, and I bet you this works. Right? Because the point is that at this point, here if we're doing right and then left, the point is that we're adding the nodes into each depth or level here, essentially from right to left. So if we make it, sorted in decreasing order, then we essentially reverse the whole thing. Because essentially it wants left to right, make it sorted in increasing order. So it's like, okay, if I'm appending them from right to left, then it's okay if I can make it sorted in decreasing order, is the very same problem, right? So that's essentially the point that I'm trying to make here. So here I'll put it back. So now we just do sort strictly increasing, but we add left and then not right. We run this again and we'll see that this works, right? So here's essentially I just populated dictionary D, where the keys are the levels and the values are a list of all the node values at that level, and specifically their values and in order from left to right, right? So like 4, 3, and then like level 3 will have 7, 6, 8, 5, then 9, 10, and it's like et cetera, right? And then I say, okay, for every single, level inside of this dictionary, that's cool. We're going to look at its values list, and we're going to say, okay, what is the number of swaps that we need in order to make that list sorted, right? And we're going to do that for every single list at every single level. So it's like, okay, for every single values array inside of our dictionary's list of values, so like, for each key is essentially an array that we need to sort. So for every single value in d.values is one of those arrays that we need to sort. For every single one of them, we're going to get the number of swaps needed to make it sorted, right? Because that's what this problem is asking. Return the minimum number of operations needed to make each value sorted level in strictly increasing order. So for every single array at every single level, we're going to calculate that minimum for that array individually, and then for each of those, we're going to calculate the sum of all those, right? For every single array, calculate the minimum number of swaps needed to between those at that level to make it sorted. We're going to do that for every single array at every single level and take the sum of all those values, right? So all that's needed to write then is just get num swaps needed to make sorted. And here I just made my life easy. I have a hash map that just maps every number to its index and every index to its number. So for I num and enumerate nums, it's like num to index of num is equal to I, and index to num of I is equal to num. Then I say, okay, at the beginning I need 0 swaps, and then I say, okay, let's sort nums to essentially see what sorted nums should be, right? And then let's enumerate over this. So essentially it's like, okay, for every single number in here, we can be assured that it's at its correct index, right? So this is why I call the index correct index, because if we sort nums, essentially every number is at its correct index, right? And then we're going to say, okay, this number is at what index inside of num? Well, here we map every num to an index and every index to a num, right? So here's like, okay, we're going to take this number, which we know is supposed to be at this correct index, and we're going to get its actual index, right? So num's actual index. If this num's actual index is equal to the correct index, good. Continue. No need to do anything or increments num swaps, right? Otherwise, it means that the number's index is not correct index, which means that it's legitimately not at its correct index, right? So what do? It's like, okay, we need to swap it with the number that is at the correct index so that the number can go to the correct index, right? So here I just do number at correct index. Let's fetch it from index to num with the correct index, right? So we get that number. Then we just need to make a swap between the number that's at the correct index and the number that is at the number index, right? And that's pretty much it. Just to make my life simple, because I was just having a brain fart moment. I think it's because I spent all day doing admin of code today that I just, my brain is fried, and my brain could not brain today, or at least for this problem today. And so I was like, okay, I don't want to think anymore. We're going to make two new variables. We're going to make it clear. Index1 and num1 is the number and its number's current index. The index2 and num2 is the correct index and the number at that correct index that we just computed, right? These are the two numbers that we want to swap. We want this number to go at this correct index. So we'll swap it with whatever numbers at that correct index, right? Because to make it go to that correct index that we want it to go to, it needs to swap with whichever number is at that correct index, right? So we just make it clear, this is the number and its index. Here's the correct index we want that number to go to, and the number currently at that correct index, and let's swap those guys, right? So here I had a bunch of asserts just because I was super paranoid. And I was like, okay, index to num at index 1 will now be num2. Index to num at index 2 will now be num1. Num to index of num1 will now be index 2, and num to index of num2 will now be index 1, right? So essentially we figuratively did that swap, so like when we check it here in the future, like, you know, it'll have the correct data because we've actually swapped the numbers. And here we of course increment the fact that we did a swap, so num swap supposed to equal 1. And once we're done with that, bada bing bada boom, we just return the number swaps, and there we go. That's how I was able to write this function and then use it obviously to solve the rest of the question in the way that I mentioned. So yeah, hopefully that solution made sense. And yeah, but otherwise, that is pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate it if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.